now I'd like to talk a little bit about reflections from flat mirrors. And so consider this surface here to be our mirror, and this surface here to be, or this line with the arrow on top, to be like a person. We can think of this as the head and this as the feet. I'm not going to attempt to draw a little man because it probably wouldn't look very realistic. And so what do we see when I look in the mirror and I see my head? I'm going to apply the law of reflection, which you'll recall is that the incident angle of the ray is equal to the reflected angle of the ray, but that's with respect to a normal to this surface. Now, since it's a flat mirror, that kind of makes it easy. So the first one I'm going to consider is a ray going straight across. Okay. So if I consider a light ray coming from my eye, and then it's going to bounce straight back because it's incident, it's parallel to a normal to this surface. Okay. Which means that when it reflects back, it's just going to come back. So that's saying that the angle of incidence is 0, so the angle of reflection is 0. Now, what about when I see my feet? Well, that means that a ray of light had to come from my foot to the mirror, bouncing off and going to my head, or my eye. So what I'm going to do here is I'm going to imagine a ray coming from my foot. And I may have drawn that a little too steep. I think I have. Let me just try that one more time. It's not the easiest thing to do, these lines. Okay, so there's the incident ray. Now I need to construct a normal to that. So I just let a perpendicular line from this mirror surface come out. So this angle here, the exiting ray, needs to follow the same angle. So I'll just kind of guess it from there. And then draw that line. So there is the ray that came from my feet, had just the right angle of incidence to reflect up to my eye so that I see my feet in the mirror. Now, let's extend this idea, because when we look at a mirror, we kind of think that we see someone on the other side that looks a lot like us, right? So what does that mean exactly? How does that work? Well, I can imagine these rays. When I see a ray coming from here, right? I see a ray coming from here. I can imagine kind of extending these rays into the background here like this, and then this ray would extend, oops, get the angle right here, something like this, right? Now you recall from before when we constructed this virtual point, as I called it, we took a point here and we imagined the same distance that we have from here to here, going from here to here, let's say, right? And we can do the same thing with our feet. We can take this point here and imagine that it is, whatever this distance is, go this distance into the mirror, and that puts us here. So our head would be up here, and our feet would be down here. And, well, I guess that was not the best place to draw it. It should have been more like this. There we are. I know the distances don't look exactly right, but that's because of my poor drawing skills up here. So we see the object right side up, so my head looks like it's in the right place. My feet look like they're in the right place, below my head. And so it appears that there's this image from behind the mirror, and these rays, which I see coming in, seem to be coming from these points, like this. So we can consider a variety of flat mirror problems using this idea. I mean, instead of using things that have height, we're going to just consider points. So let's consider the following. If I have a mirror whose edge is here, and it has another edge here, and I'm going to put some people. Call this person A, I'm going to call this person B, I'm going to call this person C, I'm going to call this person over here D. And what I want to know is who can see who in the mirror. Right? So imagine you're sitting here, who can you see in the mirror? How do we figure that out? Well, all we have to do is construct these images. And the way that we construct an image is, let me just create an artificial extension of this mirror. Right? There's no mirror there, that's just a dotted line to let us know where that surface is. And construct a parallel line from here to here. And whatever that distance is, right, when we measure a parallel from here, so here I get 13 centimeters. So I'm going to go from that same point up 13 centimeters. This will be where my image appears to be, call that A prime. Then we can do the same thing with B, which we'll call B prime, and with C. Okay, so just before the camera cut out and I changed the batteries, I was drawing these virtual images, which are the same distance. If we draw a normal to this surface, the image is the same distance behind as the real object is in front. So pretty easy to construct. And so what I've done is I've laid out these 4 dots, which we'll call students, A, B, C, and D. And now we're going to ask the question, who can see whom? Now, can A see himself? Well, the way we find out is we construct a ray going from A prime to A. And as you can see here, this does not pass through the mirror, so A cannot see himself. Can A see B? Well, if A sees B in the mirror, he'll see we need to construct a ray coming from B's image, B prime, and going to A. It looks like it can just make it. Just at the edge there. Can A see C? Well, we do the same thing. We need a longer ruler this time. We construct a ray from C prime to A. And so A can see C. And you can probably tell that A will be able to see D as well. Because when I construct a ray going from D's image to A, the line passes through the plane of the mirror. We could then ask, well, who can B prime see? Or who can B see? Excuse me. We can then ask, who can B see? Well, B, it looks like he can see A, but let's just see. Well, if A can see B, then B can see A. So my drawing is not the greatest, which is why this appears to miss. But we'll just let that come over just a bit. B can also see himself, and B can see C, and it looks clear that B can see D. C can see A. We don't need to draw all of these lines, just consider the line going from the image to the point. Looks like C cannot see D, however. It's very close, and I would say no, that's a miss. D obviously can't see himself, but D shouldn't be able to see C either. So if we construct a line from D to C, yeah, D cannot see C. So we have in the final summation here that A can see B, C, and D. B can see A himself, can see C, and what did we rule on B, C, and D? Yeah, it looks like you can see D and D. C can see A, B, C, and I think not on D. So A, B, and C. And then D can see A, B, I think C. Oops. No, we already decided that he couldn't. D can only see A and B. So the only person here that can see everybody is B, which probably makes sense intuitively, but this is how you figure these problems out for flat mirrors. And next we'll consider parabolic mirrors and spherical mirrors.